Welcome back to the second part of week 1 of quarter 3. We are going to be doing a little wave lab in which I have a bunch of stations set up. So I'm going to be moving to the back of the room here in a little bit. But before I do that, I just need to give you a little bit more information in order to know what a node and an antinode is as you see them in lab. All right, first thing, a standing wave. A standing wave is the wave pattern that results when two identical waves travel in opposite directions and then interfere with each other. Interfere. All right, so what happens is one wave goes, it hits something, reflects back, and moves backward in the opposite direction. So they're identical waves moving in opposite directions, and they cause interference with each other. Okay, when this happens, you get a wave pattern called a standing wave. Okay, so it first starts, I'm going to use a slinky. I'm going to start by just moving it up and down. Okay, so this is a standing wave. I'm moving just this hand right here, and it's moving up and down, creating this standing wave. All right, on the standing wave, you'll notice that there's two places where my hands are that don't move very much, and then there's one place right in the very center that moves a ton. Those places have names. All right, they are called the node and the antinode. The node is a point on a standing wave that has very little movement. So it does not move very much. It was where my two hands were. So in the case of right here is a node and right here is a node, the two fixed points are going to be your nodes where my two hands were. In the center, where it moved up and down, so this is just the slinky moving up and down, that's called the antinode. It's a point on the standing wave with maximum vibrations or lots of movement. And that was in the center place. Okay, now what I can do is I can move my hand a little faster, and I can create this wave pattern that looks more like this infinity symbol. Or if I go super fast, I can get it to go like that. So I can create more nodes in the center of my wave. Okay, so I start off just doing normal things, and then if I speed it up a little, I've got this wave pattern that still has two nodes on either end, but it now has a node in the center as well. Okay, it also has two antinodes. I have a spot right there and a spot right there that have a lot of movement, that they're moving up and down a lot. All right, if I go even faster or you have a longer slinky, you can get even more nodes to occur. All right, and that's what a standing wave is. It's that wave pattern that results when two identical waves travel in opposite directions and interfere. Okay, you might want to know, why is this important? Well, the cool thing is, if you play any sports in which you hit a ball, then you are using nodes to your advantage. Okay, if you are baseball, softball, a golfer, a tennis player, okay, when you hit the ball at the node, you've hit the sweet spot of the racket, the golf club, or the bat. Okay, it makes the ball go farther. When you don't hit the node, you hit an antinode, you feel lots of vibrations. So if you've ever hit around the edge of a tennis racket, hit the ball there instead of in the middle, okay, you feel that in your hand. If you've ever hit a ball and you hit it kind of at the top or the bottom on the barrel of the bat, you feel those vibrations and it hurts your hands. Okay, what you're doing is, when you hit the sweet spot, you have found a node. Okay, so the sweet spot on a bat, or a racket, or a golf club is due to nodes and antinodes. When the ball hits the bat, vibrations occur. Or the club, or the racket, whatever you want to talk about. Okay, these vibrations set up a standing wave. Even though it's inside of the solid, that's okay, there's still waves happening in there. Okay, it sets up a standing wave with areas of nodes and antinodes. If you look at a bat, it actually sends up, here's the handle, and here's the end. Right here, right at the sweet spot of the bat, that is a node. Okay, if you hit it here, here, or down at the handle, you are hitting it at not a node, so it hurts. you have a lot more vibration. So if you hit the ball at the node of the bat, it won't vibrate and it won't lose energy. You'll have more energy to put into the ball, and that's why it goes farther. If you hit the ball at the anti-node, there'll be lots of vibration, which wastes energy, and the ball won't go as far. All right, so those are examples. We need to know what a standing wave is, that wave pattern, and then what a node and an anti-node is in relationship to sporting equipment and different things. All right, for the different stations, the first station, we are going to test your hearing. I don't know how well this is going to work on YouTube. It does cut out with high frequencies, so we're going to do what we can. If you're on Zoom, you'll be able to hear it coming out of my computer. All right, so earlier this week, we learned that humans, on average, our species, can hear in the frequency range of our low end is 20, and then our high end is 20,000. This is the audible range. We can usually hear somewhere in that range. Not everyone can hear all the way down to 20, and not everyone can hear all the way up to 20,000. Okay, so we're gonna test your hearing. So first thing, I am going to switch over to my computer, and I'm gonna hook up the sound. Now, the problem is, with the sound, you're going to hear a background. Sometimes you can hear a background hum in my classroom coming from the speakers. Okay, what I'm going to do here is I'm going to play this, and it's going to start sending out a frequency that starts at 20 hertz. When it starts to work, you'll start to hear a really low humming sound. Okay, you are going to take note of what number is up on the board when you start to hear that humming. All right, so I'm going to get it started. You're listening for something that sounds like a low humming. This is where it kicks in for me, at 40 hertz. Kind of just sounds like a motor engine starting to warm up. Let it go a little bit longer. But usually if you were in the classroom, everybody would have caught it by now. All right, now what I'm gonna do is I'm gonna switch over to the high notes. Okay, so I'll give you a little preview. All right, that's what we're gonna start to hear. Okay, so I am going to start with an 8,000 hertz. If YouTube is working great, you should be able to hear a really high-pitched noise. Okay, we're going to keep playing it until you can't hear it anymore, and then you're going to write that down. So that was 8,000. Here's 10,000. Here's 12,000. It should just get higher and more annoying. All right, now here's the funny one. The 14,000, I can't hear a sound. There is nothing, no high-pitched noise, nothing when I play it. If you can still hear it, then you can still hear it 14,000. Okay, here's where YouTube might make this harder for us. YouTube tends to cut off because they figure nobody needs frequencies up above 15,000. They tend to cut it off so that you can't put anything on YouTube higher than that. So I don't know if this is going to work, but I'm going to play 15,000 and then the other ones. And if you can hear them, you're good. And if not, it's because either you can't hear it or YouTube isn't letting you. So here's 15,000. Here's 16,000. All right, 17,000, I'll play it twice. And then 18,000 is usually where people in the classroom start to kind of sit down, unless they're like me and can't hear that well these higher frequencies. $19,000, $20,000, and occasionally a person can hear a 21,000, but not very often. All right, none of those I could hear, so I can't even tell you if they're there or not. Like I said, if YouTube didn't make it work, just estimate or put 15,000 whenever you stopped hearing it. You can always hop into the Zoom and you'd be able to hear it better from my computer if you would like to. Okay, I'm going to pause and then I'm going to move our location to the back of the room. Okay, we are on to station number 2. Any type of glass. So at home, if you want to get an extra sticker, you can do this with any 3 glasses or more. Fill them with different levels of water, and then you're going to take a picture of it and you're going to send it to me on Remind, and I will get you an extra sticker. Okay, if you don't have anything in your actual vicinity, you'll just use what I'm doing right here. So find 2 or more of the same type of glass. They have to be made out of glass. And fill them with different amounts of water. Carefully hit each glass with a spoon. I'm just using a glass stirring rod. Okay, there's 2 questions that goes with it. Which one makes a higher pitch? The one with more water or less water? And knowing if frequency and velocity have a direct or an inverse relationship. That's not the one we've talked about before. They have a direct relationship. They are on opposite sides of the equal sign. If the velocity goes up, the frequency goes up. If the wavelength remains the same. If they go down, they go down. All right. So I am going to hit the glasses. This has more water, less water. More, less. All right, so hopefully you can figure out the pitch and how that changes, and then I give you a little information behind it along the way. Station 3, boom whackers, that is these guys right here. So you can actually play, I have a full octave right here. You can actually play a song. But what ends up happening is inside of these boom whackers, when you hit them, inside the air starts to vibrate and it sets up standing waves. Equal to the inside is a portion of the wavelength. The shorter this guy is, the shorter the wavelength of the wave. Okay, so this guy and this guy, this has a shorter wavelength than this does because it has much, less length involved. All right, so then as you're playing your actual song, I had them on order, that was terrible. But if you'll notice, it starts with a high note and gets lower as it gets longer. The shorter it was, the higher the note, the higher the frequency. So you're going to look at the relationship between frequency and wavelength, it's inverse, and see what happens for that. Station 4, another wine glass. This one works a little bit better for me, so I'm going to try and get this to, it's called resonate. If you can find a wine glass, you need it to have a stem and hold down, not the actual stem, hold the base of it. From there, you're gonna get your finger a little bit wet, and you're gonna go around the outside of the glass and make it sing. All right, what you're doing is, I'm creating vibrations. Next week, we're gonna learn that those vibrations are actually matching the frequency of the glass, and it creates some vibrations and it amplifies the sound, creating, it's called resonance. All right, but for now, you just need to know that I am making vibrations in the glass and make the wine glass sing. See if you can do it. It's hard, and you have to have some glasses that are a little bit easier than others, but give it a shot. And then finally, station number 5, a standing wave with a slinkly. I already showed you this in the standing wave notes, but see if you can, get it to do that, and then see if you can get it to do that if you have one at home. If you don't, you'll just kind of have to use what I'm going there. You're going to point out the places of the nodes, not much movement, and antinodes where there's a lot of movement, where maximum vibrations are occurring. All right, for the end of the lab, there are some review questions, mostly definitions or the units things are measured in. Getting that done and getting that submitted will get you points for class this week as well. All right, so quick reminder, there was a little introduction to quarter 3 that you need to click through to get the points for the beginning of the week. That was on Zoom. Then there were the wave notes that went with problems. The problems need to get submitted. I don't need the notes. You can separate them if you want to. Then there's the wave lab. You are going to swap that, complete that, and get that submitted to me. And then finally, there's an end of the week wave check for understanding to make sure you know the important things for the week. Thank you very much. I hope you enjoyed. I know it's not really lab, but I'm doing my best.